Data used for this work comes from a user study from prior work, a collaborative task with Baxter Robot. 3 robotic failure actions, each resolved by human actions. Pick failure resolution action is human handing over object to robot. Carry failure resolution is robot to human handover, human placing object in shelf. Place failure, the human takes object from robot and places it at the correct place in the shelf. Robot explains that each failure and explanation levels are as shown with explanation strategies, particularly 2 types, fixed and decaying strategies. In these examples, we see how insufficient information in robotic failure explanation leads to confusion induction in users, absence of information because of medium-low level explanation, or reduction of information due to decaying explanation strategy leads to confusion induction. To adapt explanation, robots should first observe human behavior at failure. Across different phases of human reaction, we process the raw data to output emotion, likelihood, gaze, and gestures. Here's a snippet for the data collection. We collect the data for gaze of participant, whether he looks at the robot or task or elsewhere at a particular instant. Further, we also recognize some gestures, including head touching and head tilting, which get true or false values. Further, we use Hume AI to process the likelihood of certain negative and positive emotions. Negative emotions including stress, doubt, distress, disappointment, anxiety, anger, and confusion, and positive including satisfaction, interest, desire, and contentment. The output is the likelihood of these emotions being present on a scale of 0 to 1. The likelihood of confusion emotion is used for our automated approach to identify confusion induction, where we check for high confusion and persistent confusion for each interaction and for each user. And this is an example for high confusion. We see in the plot for confusion likelihood value that the confusion likelihood value reaches above a set threshold for high confusion at this point in the resolution phase. This is an example of persistent confusion where confusion increases in failure and explanation phases but does not decrease in resolution phase. We see in the plot that the values increase in failure and explanation phase, but instead of decreasing, it reaches a new high in resolution phase. Upon observing human behavior at failure, robots should now predict confusion induction for failure explanation. We formulate a predictor to assess if decrease in explanation results in confusion induction. This example predictor outputs the user to be confused with a decrease in explanation. And we see that with decreased explanation, user is identified as confused with the failure not resolved. Finally, the robot should use the predictor to adapt its explanation. Decrease the explanation level if predictor outputs user not confused with a decreased level. Increase the level if predictor outputs user confused at same level. Else keep the level same.